Okay, today let's start our last chapter. It is another one on applications of integration, and this is the areas between curves. Okay, so instead of finding the area between one curve and the x-axis now, which is what you've been doing before, you'll be finding the area of a region, usually between two curves. So we're going to look at a few graphs to understand how to do this. I'm going to point some things out. So what you're used to is setting up an integral to find the area under this curve. So since this says y equals e to the x, remember you used to write area is the integral of e to the x dx from 0 to whatever this number is. So we're going to call that b. And that's how you would find the area under that curve. Now also remember that areas quote-unquote under a curve actually mean the area between the curve and the x-axis. For the area between the curve and the x-axis, if you have areas above the x-axis, they're positive, and areas below the x-axis are considered negative. And this graph is talking about, excuse me, if this is your function, then this is velocity over time. One of them gives you displacement, one of them gives you distance. And then finally, we haven't really looked at graphs like this. I don't think very much in class. I don't remember if you had any for homework, but you could try to rewrite this as y equals a function of x. A lot of times it's not possible, but the same principle here, if we went, the area between this and the x-axis, we can find the area between this and the y-axis. What you're actually doing, and I want you to understand this before I turn the page, is let me go back to something familiar. We're looking at the area between this curve and really this curve, right? What is this if you wrote this as a function? It's a horizontal line, so it's y equals. Where does it go through? It goes through 0. So that's the line y equals 0. So you can think of this as we're taking the area of the top minus the area of the bottom. It might look a little weird, but you'll understand it, it might help the rest of this stuff to make some more sense. Similarly, we can look at this function as x equals 2y minus y squared, and then we can look at this as x equals 0. So we can take the integral of the right side function, what does this look to be, from 0 to 2, and we could subtract, it keeps looking like I'm making a plus sign, we could subtract the integral of the left function. Okay, now in this picture we want to try to understand how to find the area of the region S. Okay, so if you can see, the pink curve here is let me point to it. The pink curve here is y equals f of x. So if I find the integral of f of x dx, let me try to match that color a little, then I'm finding this area, right? That's the integral of this function. Gives you the area between that top curve and the bottom curve. If I just want the area of the region S, though, and I don't want the whole thing, then I would take away the blue part, right? I would want to take away this area right here. And if I subtracted that red area minus this blue area, then I would get, again, the area that I'm looking for, okay, just the S. One way we can do this is we can take the area of this curve and then subtract from it the area under this curve. When you're integrating, if you just think about properties of integrals with the way you've learned things, if I want to take an integral minus an integral, I can just take f of x minus g of x and integrate the whole thing together. That would be quicker because if I integrate this function by itself, I'm going to have to do my fundamental theorem of calculus and do capital F of b minus capital F of a. Then over here I'll have to do capital G of b minus capital G of a if we use that antiderivative notation. But if I put the curves together, then that's going to be, like I said, more efficient. So right here, the area is going to be the integral from a to b of f of x minus g of x dx. If you are taking notes, I would definitely pause and write this down. This is how you find the area of a region bounded by two curves, f of x and g of x, where f is on top and g is on the bottom. That's basically what this says. F is on the top and g is on the bottom, from x equals a to x equals b. Okay, that's your formula. Okay, so let's look at some examples. All right, so I graphed this on Desmos, so I would imagine you guys are probably going to graph these on your calculator. The directions say to sketch the region enclosed by the given curve, so here it is. Decide whether to integrate with respect to x or y. We'll look at both. Draw a typical approximating rectangle. That's one thing we're not going to do. Label its height and width. And then we're going to find the area of the region. Now, you can read through the book if you want to see some examples of sketching a rectangle, but I've never really noticed that or found that anyone finds that makes this process easier. All right, so what we're trying to do is can I make this thicker so we can color this in? Yeah, I'm going to make this thicker. All right, so what we're trying to do is find the area right in there. All right. So to find that area, we want to use the formula that we just were given, which is the area of the top. You see how the top is blue here, right? So the top is blue. So 1 minus x squared is the top function, minus x to the fourth minus x squared is the bottom function. And we are trying to find that integral from here to here. Now you can see on the Desmos graph that goes from -1 to 1. Let me start to talk about how you're going to find those points. On your calculator, if you use your calculator to find those intersection points, because you do need to know where these two graphs touch each other, you can put one of these functions in as y1, put one of these functions in as y2, and then do second trace, because that's your calculate menu, and then do isect for intersection point. And you'll get, in this case, that your two intersection points are -1, 0, and 1, 0. You can also do this analytically if you don't have a calculator, meaning we can use substitution here. We can say, okay, I could solve for, well, these are already solved for y. So I have x to the fourth minus x squared equals 1 minus x squared. And add x squared to both sides, so you get x to the fourth equals 1. And if you solve that, you get x equals plus or minus 1. And then you can plug that in for x to get y. And you would get 1, 0, -1, 0. So you can solve these, analytically, or you can solve them with a calculator. As far as the integration goes, that's the same thing. Right now, I can integrate this. I can distribute the minus sign through, and I can make this, let's see, that's the only constant, minus x squared minus x squared. That means minus x squared plus x squared, it's gone, minus x to the fourth. And then I can actually use my integration rules. But you can also integrate on your calculator. You don't have to do any of this if you want. This is all from here on out for me, unless you want the practice for this for the AP exam. I'm going to let all of that be optional. All you really have to do is put this in on your calculator. Using, do you remember that's Math 9? And I'm going to get that on my calculator. Okay, if you have your calculator handy, remember it's Math 9. Your function, since we did already figure this part out, you can use it of 1 minus x to the fourth. Otherwise, you can put this whole thing in. With respect to x, from -1 to 1, and you get 1.6, and then if you hit Math Frac as a fraction, that is 8/5. And that's your answer. That's your answer for the area. Okay, since this is just a video, pause it and, go back through things anytime you want. All right, here, I want to try to leave some spots for questions for a play pause it. So would I go, okay, this is a problem from your book where they already give us the picture. All we have to do is use what they give us in the formula that we have. So we have that we could do the integral of the top minus the bottom from the left to the right. Okay, hopefully that's not too messy for you. Now, I said before that actually figuring out the integral by hand was optional. Here it's not going to be optional, and there's a reason why. If you think about when you integrate square roots, you can get square roots in your answer. When you plug in a 2 eventually, whether we have the square root on the top or on the bottom or whatever, if we have a square root and we plug in a 2, square root of 2 is 4. 4 can be turned into a fraction. But when we plug in a 0, that means at some point we're going to have a square root of 2 in our answer. Having a square root of 2 in our answer is going to make it irrational, which means the math frac button won't work. So if we don't get a rational answer, I would rather you not work this out on your calculator. The same thing is going to happen over here because this is like a 1 over u du, and the integral of that is the natural log of u. So we're also going to have a natural log of something, and that's also going to be an irrational number. So we do have to work this one out by hand. All right, you can think of little u substitutions. I hope you can see. Of course, I don't know how rusty your calculus is at this point. We've been gone for a long time already. For this part, that's going to be my u. For this part, I'm treating this sort of like two different problems. This is going to be my u. But you'll see in both of these, like, I don't have to worry about coefficients. I don't have to worry about kicking out a negative sign or kicking out a 1/2 or a, anything like that. So this is just, I'm just integrating u to the 1/2, and I don't need to worry about any coefficients. Here I'm just integrating 1 over u. I don't have to worry about kicking out any coefficients. So this integral is just u to the 3/2 over 3/2, which you remember we write like that. This is just the natural log of u. And I'm going to go from 0 to 2. All right, so let's plug in our 2. You can maybe, pause and try this yourself, and then play the video when you're done and see how well you did. All right, so if I plug in the 2, I'm going to get a 4 to the 3/2. That says 3/2. I'm not going to try to erase that and make it look neater. This is the natural log of 3. Remember, fundamental theorem of calculus, this is my f of the top, and now here comes my f of the bottom. 2 times 2, when I plug in a 0, to the 3/2 over 3. Minus the natural log of 1. Okay, so what is 4 to the 3/2? All right, 4 to the 3/2 means take the square root of 4, which is 2, and then cube it, and that gives me 8. 8 times 2 is 16/3. Okay. Over here, this one gets a little, just you have to be a little more thoughtful on this one. You're taking the square root of 2, which is the square root of 2, and you're cubing it. Or you're taking 2 cubed, which is 8, and then you're square rooting it. Either way, that would simplify to 2 times the square root of 2, and then I'm multiplying that by 2. So that's going to be, not what I was about to write. Okay, 4 times the square root of 2. And then what is the natural log of 1? The natural log of 1 is 0. All right, so we're finally almost done. This is going to give us 16/3 minus the natural log of 3. I was thinking that was minus. I mean, I guess I just kind of wrote the same thing twice. I could edit this out, but I probably won't. We could get a common denominator, right? Maybe here and here. So 16 minus 4 times the square root of 3 all over 3 minus the natural log of 3. That's your answer. Now, a neat thing you can do is work this out on your calculator and then work, what else? And then do actually this integral on your calculator, and you should see the same decimals. Maybe that's what I'll put in for the play pause it. What are those things as decimals? Okay, 16 minutes in. How you feeling? Get up and stretch. Take a break. Okay, when you come back, let's integrate this one. Now, these functions here are in terms of y. So to get a positive value, because this area is always going to be positive now no matter where it is, up here, down here, to the right, to the left, all these areas are always considered positive. I feel like I did not say that on the first few slides. So I am going to integrate here right minus left from the bottom to the top. So I'm going from 0 to 3. These are y bounds because I'm using y functions. Right minus, oops, I should probably put in some parentheses there. Right minus left. And that's it. Now, this is just a polynomial thing here. And be careful, that kind of looks like a cubed, but that's the squared. Because it's a polynomial function, again, I could put this in on my calculator. You do not need to use y's. Your calculator, I mean, think of this variable as being called what we would we would call it a dummy variable. It doesn't really matter what letter you use. You can put this into your calculator using x's, and that will give you the answer just fine. So I'm going to do that, and I am just going to write down my answer. Okay, hopefully you let yourself try to type that in. I personally just put in math 9, and then for my function I did 2x minus 2x squared plus 4x. I combined like terms, and you get an area of 9. You don't even have to turn that into a fraction. Okay, the last kind of problem. You have a few at the end of your book, and this is out of your book, where you're just given a graph or a table. In this function here, we're given the graph. I actually took the example, but I just wanted to talk through the example in the book because there's not a lot of exercises to pick from here. This says we have the velocity for 2 curves. Now, this is given in miles per hour, or 2 cars, my bad. Cars A and B that start side by side and move along the same road. What does the area between the curves represent? And use Simpsons Rule to estimate it. All right, so what do we get? Let me try to make this a little bit thicker again. Okay, so if I look at, because it's easier to see if I start with car B, if I look here, what is this area? Well, if I'm careful with my units, and I make my units here, if I turn them from miles to hour to, say, feet, definitely want to make that there now. If I make that feet per second, and that would be for my height, right, of any rectangle. If I looked at a rectangle here, my height would be given in feet per second. My base would be given in feet, or in seconds. My base would be given in seconds. So that would give me my total amount of feet. If I added rectangle areas together from 0 all the way up to 16, I would get how many feet I traveled in the first 16 seconds. So really, we've answered the first question. What is the area between the curves? Well, between the curves. All right, so if I look at B, I see how far B has gone. If I do that same type of thing But with curve A, then I would see how far A has traveled. Well, can't, if I look at the area between two curves, wouldn't that just be how far A traveled and then subtract from that how far B traveled? That would still be feet, feet minus feet. So that would give you how much farther, in feet in this case, how much farther has car A gone than car B. All right, so that's the answer to the first question. All right, now if we're going to use Simpsons Rule to estimate it. All right, you remember Simpsons Rule. Simpsons Rule, generically, is that an area, I guess I should say approximately equals, B minus A over 3n, and then we need our first y value plus 4 times the next y value plus 2 times the next y value plus 4 times the next one. And we have coefficients 4, 2, 4, 2, 4, 2, 4. It has to end with a 4 for the second to the last coefficient. And then your last term does not get a coefficient. So that's Simpsons Rule. Okay, we did that a little bit before you guys left. That was the end of chapter 5. All right. Okay, so what are these f of x's here? These are y values. So I can find y values here by, looking at these. Now that's not in miles per hour though. So you can see how if I'm taking times in seconds and I'm multiplying it by all these y values, but these y values are in miles per hour. Do you see how I'm going to mess things up a little bit. So what they do here in the example, cut a little bit of time off the video by showing you this, is they change all of these velocities, say at 2 seconds. Car B is 21 feet per second. Instead of using this, what would this be, about 14 miles per hour? Okay, something like that. So they changed for all of these things. Again, this is like right here. So they changed about 28 or 29 miles per hour into 34 feet per second. So they made a table. So that would be one thing that would make this thing a little bit easier for you. Another thing to think about is for Simpsons Rule, instead of doing Simpsons Rule, which is going to take pretty long here, if we're going using, for my x values, we would use, or t values, we would use 0, 2, 4, 6, 8, 10, 12, 14, 16. We would have 0 times, a coefficient of 1 for this y value, coefficient of 4 for these y values, coefficient of 2, 4, 2, 4, 2, 4, and then a coefficient of 1. And we can do the Simpsons Rule for car A minus the Simpsons Rule for car B. But if you think about it, a quicker way to do it would be just to make this nice little column and then only have to use Simpsons Rule once. So instead of doing two separate integrals and subtracting them, you can do an integral of the difference, much like we did, just to get the formula of areas in general. Hopefully that made some sense. If you want to finish this, you can, and then you can check your work in the book because it is example 4 in Stewart. I'm done. I'm going to go throw some questions in this, and then this is your lesson.